Hello everyone and welcome to another lecture of Machine Learning Foundations. We will continue with the univariate calculus ideas that we had begun last class. In this class we will mainly focus on the derivative and its link to what are called linear approximations. Right. So let us consider a differentiable function from R to R. Right. So let f from R to R be a differentiable function. What is the definition of the derivative? Well, f dash of x star is equal to limit x approaching x star f of x minus f of x star by x minus x star. So, we do have a limit term here. So, we can't do direct multiplication by x minus x star and move, you can't move this here, but let us assume that, right. So, let us assume that x is approximately equal to x star, that is we are in a regime where x is approximately equal to x star, in which case the limit x equal to x approaching x star is satisfied. So, we can say that f of x star is approximately equal to f of x minus f of x star by x minus x star in the neighborhood around x equal to x star. So, this is true only when x is approximately equal to x star. Only then we can remove this limit statement without affecting logic. Now that we have this, we can move things around and write an alternative expression, which is f of x is approximately equal to f of x star plus f dash of x star into x minus x star. So, f dash of x star is approximately equal to f of x minus f of x star by x minus x star around x equal to x star, which means that f of x is approximately equal to f of x star f dash of x star into x minus x star plus f of x star. This is also true around x is equal to x star. Right. When x is close to x star, this is true, right, and this is called a linear approximation. Right. So, you can view this, the left hand side is a function of x, the right hand side also can be viewed as a function of x. You can view x star and f dash of x star as constants, which means that f of x star is a constant, f dash of x star is also a constant. This entire term also can be viewed as a function of x, and we are going to denote that by L x star of f. So, this entire thing is a function of f, and if you want to evaluate it at a point x, so it is L x star of f of x. So, what the approximately equal to statement says is f of x is approximately equal to L x star of f evaluated at x around x is equal to x star. This is the key idea, the key expression in essentially first order calculus. Right. So, this is f of x can be approximated by f of x star plus f dash of x star into x minus x star around x equal to x star is the key approximation idea that we will be using for a major part of machine learning. So, what does this mean for us? Right? So, let us give some graphical illustration of this. Let us consider the simple function f of x equal to x squared, which we know to be differentiable, and let us pick some x star is equal to 1. Right? So, let us pick x star is equal to 1 and consider the point x star comma f of x star. What is f dash of x star? F dash of x star is simply equal to 2, right. That simply follows from calculus. So, f of x is x squared, f dash of x is 2x, f dash of x star is 2. Right. So, now we can write down what the linear approximation actually is. What is the linear approximation? Well, Lx star of f is simply equal to f of x star plus f dash of x star into x minus x star, which happens to be 2 squared plus 2 into x minus 2, which is 4 plus it is 1 squared plus 2 into x minus 1, right. So, we said x star is equal to 1, right. So, 1 plus 1 squared plus 2 into x minus 1, which is 1 plus 2x minus 2, which is equal to 2x minus 1. So, what we are saying is the linear approximation of f around x around 1 around x equal to 1, this is valid around x equal to 1. This red line corresponds to the graph of 2x minus 1, and you can see that this particular graph is an approximation to the black curve, which corresponds to x squared around x star is equal to 1. So, you can see that at x star is equal to 1 it exactly touches it, it is exact. The farther your x moves from x star, the worse your approximation is. Around x is equal to x star, your red line and black line coincide quite well, right. That is the reason why it is a linear, it is an approximation. As your x moves far and far away from x star, it becomes a bad approximation. For example, at this point, let us say x is equal to 2, you can see that there is actually a gap between f of x and Lx star of f evaluated at x, right. So, this point here corresponds to x comma Lx star of f evaluated at x. So, that is the reason why I am saying that Lx star of f is an approximation of f around x equal to x star, right. So, that is what we mean by saying that Lx star of f is a linear approximation. And why is it a linear approximation? You can see that Lx star of f, the graph of Lx star of f is a straight line. Why is that? Because this is 2x minus 1, this is a linear function of x, the coefficient is it is an equation of a straight line. In general also it is true because you can see that Lx star of f viewed as a function of x is simply the coefficient is f dash of x star, which is a constant. You have this is a constant and a constant times x, and f dash of x star into minus x star is also a constant. So, f of x star plus f dash of x star f of x star minus f dash of x star into x star is a constant. It is a, and you have f dash of x star into x, which is a linear coefficient of x multiplied by x. So, that is the reason why this is called a linear function, and this is an approximation of f around x equal to x star. Right. So, that is about linear approximations, and you can you would have also seen another interpretation of linear approximation via what is called tangent lines. So, tangent is a geometric object, while a linear approximation is a functional object. What is a tangent? Well, a tangent is I will geometrically define, vaguely geometrically define one set is a tangent to another set if it touches the other set, right. So, if we can say a line is a tangent to a set if that line touches the first set. I am not going to define touching in a formal sense because that is way too much work, but it is in this case you can see that the red line, which corresponds to the graph of the linear approximation of f around x star, is a tangent to the graph of f, right. Or in other words, I am going to write it in a formal way, which is your graph of Lx star of f. Lx star of f is also a function, So, the graph of that function is also going to be a subset of R2. In the case of functions from R to R, this is a subset of R2 is a tangent to the graph of f. Gf at the point x star comma f of x star. So, this point is the point at which these two sets touch each other, that is x star comma f of x star. This is the definition of a tangent line, and linear approximations to form tangent lines to the graph. The graph of linear approximations form tangent lines to the graph of the function. Right. Okay, here now we have the basics of linear approximations and tangent lines. We can see some examples. Right. The first example is perhaps the most famous one. Linear approximation, give the linear approximation of f of x is equal to sin x around x star, which is equal to 0. Okay. So, to do that you need f dash of x. What is f dash of x? F dash of x is simply cos x. F dash of x star, which is cos 0, which is 1, and f of x star, which is sin 0, which is 0. With these three facts put together, we can say f of x is approximately equal to f of x star plus f dash of x star times x minus x star. What is that? Which is 0 plus 1 into x minus 0, which is 0. And when is this valid? This is valid around x is equal to 0. When x is close to 0, this is a valid approximation, or in other words it says that sin x is approximately equal to x if x is approximately equal to 0. This is the famous sin theta by limit sin theta by theta is equal to 1 thing that you would have derived in your school. Let us do one more classic expression for that. Let us say f of x is equal to e power x. Right. I want the linear approximation of this function around x star is equal to, let us say, 0. In this case, what will be e power x then is approximately equal to e power 0 plus x minus 0 into f dash of 0, which is equal to 1. So, e power x is approximately equal to 1 plus x around x is equal to 0. So, I am going to highlight the fact that e power x is approximately equal to 1 plus x is true only around x equal to 0, and I am going to highlight that. Similarly, this also deserves a highlight. So, a few more classic examples. Let us do what is log of 1 plus x. Around x star is equal to 0. F of x equal to log 1 plus x. What is f dash of x? F dash of x equal to 1 by 1 plus x. F dash of x star is equal to 1 and f of x star is equal to 0. So, we can put all that together and say log of 1 plus x is approximately equal to log of 1, which is 0, plus f dash of x star, which is 1, into x minus 0. So, log of 1 plus x is approximately equal to x around x is equal to 0. So, we will do one more example. Let us say f of x is equal to 1 plus x power r. R is some integer, let us say 2 or 3 or 7, it does not matter. So, 1 plus x power r around, we want to approximate 1 plus x power r around x is equal to 0. Okay. So, what is f of x star? F of x star is equal to 1. F dash of x in general is simply equal to r into 1 plus x power r minus 1, and f dash of x star in particular is going to be equal to r. Right. We can put all of that together and say that 1 plus x power r is approximately equal to 1 plus r into x minus 0, right, just 1 plus rx. And this is also valid around x equal to 0. Great. So, this should give you a idea of all pretty much lot of calculus makes approximations very easy to write down, right. So, which is e power x is approximately equal to 1 plus x around x equal to 0, log 1 plus x is approximately equal to x around x equal to 0, and so on. You can in general apply this to any function that you have. You want an approximation around which is valid around a particular point x star, you can just use f of x star plus f dash of x star into x minus x star. And the advantage of the linear approximation is that it is a much more simpler object than the original function. And this is going to be the key idea that is going to drive most of optimization. Okay. Let us apply this particular idea for a simple question. Now here is an exercise question. Which of the 4 options, now this is an exercise option. I want 0.99 power 7. Right. Which of the 4 are closest to 0.99 power 7? The 4 options are A is let us say 0.95, B is 0.93, C is 0.91 and D is 0.9. So, you have 4 options here and the exercise is to find which of these 4 options is closest to 0.99 power 7. Neither of these are exact, but the question is which of these is closest. So, 0.99 power 7 should immediately think of 1 plus x power 7 where x is equal to minus 0.01, and minus 0.01 is close enough to 0 that you can apply a linear approximation, which means that 0.99 power 7 is very easily approximated by 1 plus 7 into minus 0.01, which is 0.93. So, 0.93 is a good approximation. So, you can immediately get an answer of 0.93 for a complex thing like 0.99 power 7 based on linear approximations, and intuitively it makes sense. So, 0.99 power 7 essentially corresponds to a 1% decay of let us say your money in a bank every year. What this asks is after 7 years how much would your how much loss would you have made or how much money would remain in the bank. A first cut approximation would say, well, there is compound interest happening, but it's 7 years is a small enough number of years and 1% is a small enough percentage that I can say that 0.99 that is after 7 years I would have lost 7%, which means that I will be left with 0.93 of my original money. Linear approximation essentially makes this a more formal way. I mean, what approximation are you by approximating compound interest by simple interest? What you are doing is essentially linear approximations, and this is a valid approximation as long as the rate of interest is small enough. That is, in this case, minus 1% is a small enough rate that you can do this in a valid way. And later in our later we will see that this is not always valid, and in fact for large enough, let us say instead of 1% loss we had like 10% loss, this would no longer be true because of the same reason why Lx star of f is only an approximation of f around x equal to x star. As you move farther and farther away from x star, your Lx star of f evaluated at x is not going to be exactly equal to f of x, it is going to be different from f of x. Right. So, with that we have come to the end of derivatives and linear approximations. We will have a look at some slightly more advanced rules and applications of the derivative and linear approximations now.